So this is special right triangles number 4. Okay, what do we know about special rights so far? What kind of triangles are they?
Right triangles.
Okay, good. The prior triangle we called 30, 60, 90. Why did we call it that?
Because those are the angles of the triangle.
Those were the 3 angles of the triangle. Okay, so now we're going to switch to the second of the special rights. And if its name is... What do you already know about the triangle? 45, 45, 90. You with me? So, let's draw this one. There's our 90. And I'm trying to make, although I'm not doing a very good job of it, I'm trying to make this side length the same as this side length. Why? Because this angle is 45 degrees, and this angle is 45 degrees. When we have 2 angles of the same measure, these things have to open up to this distance here, and this one has to open up to this distance. Does it make sense to you that the legs of a 45-degree right triangle are equal length?
Wait, what?
So this side is across from the 45 here, and this one's across from the 45. Does it make sense to you that these 2 sides are equal length? In other words, when you're doing your angles, this is 90, right? Everybody do this with their hands, do this. And then do a 45. Are you right in the middle? Trying to go halfway? Right, okay, here. How many degrees have I rotated?
90.
So here's 45. It has to be right in the middle. Are you with me? I don't know if that's explaining it any better. But what happens is, as you expand out to this side in its length, and as you expand out to this side in its length, these lengths have to be the same. So if this one's x, how long is this one?
X.
And so if that were 5, this were 5. Both those legs of the 45, 45, 90 triangle are equal lengths. Is this okay? Okay. So where do I want to go from here? Oh, the 30, 60, 90, I kind of like to start with that because it's got 3 different side lengths. Now with the 45, 45, 90, it's actually a simpler special right because you only have 2 lengths. If it was 5, if x was 5, these would fill in 5 and you'd only have one other length. It's the hypotenuse. Now this has to be longer. So it turns out the ratio comes out to be x square root of 2. That's the length of the hypotenuse in the 45, 45, 90. That's its ratio. When I was a student, I would always mix up the 30, 60, 90 because it's got the x square root of 3 in it. And the 45, 45, 90 because it's got the x times the square root of 2 in it. And I would mix them up and start, I couldn't remember, is it the square root of x square root of 2 for this triangle or x square root of 3? So here's how I finally remembered it. In the 30, 60, 90, you have 3 different side lengths, and it's the one that incorporates the square root of 3. Does that make sense? This one only has 2 different side lengths, so you're going to use a square root of 2. And that's not the reason why, it's just a memory device to remember when you're using the square root of 2 and when you're using the square root of 3. Is that okay for now? At least for the moment? Okay, so this is your pattern for the 45, 45, 90. All right, there it is. So if we do, let's try to draw these a little better. If this side is 6, how long is this side?
6.
If this side is 7, how long is this side?
7.
If this side is 8, how long is this side?
8.
Okay? You with me? It's so far even way simpler than the 30, 60, 90. Come across here, how long is the hypotenuse?
6 radical 2.
Everybody say 6 times the square root of 2.
6 times square root of 2.
And then also say 6 radical 2.
6 radical 2.
Those are synonymous. You can use whichever one you like. You can say radical, just 6 radical 2. You could say 6 square root of 2 or 6 times the square root of 2. There is a times between there, which might help your brain to hear that, right? What is the length of this hypotenuse?
7 radical 2.
What's the length of this hypotenuse?
8 radical 2.
So imagine all of our phones disappeared and all our calculators disappeared. And we still had to build buildings to shelter people. What types of triangles would you use? You'd use the special rights. You don't need calculators to calculate the length of those sides. Are you with me on this? That's the genius of it, and that's why they're called special rights. All right, now let's go to the more difficult situation. How long you want to make the hypotenuse? Let's make it up. We'll design our own problem. How long you want to go on it? And actually give me an even number first. We'll do an odd number second. Say it again. 14, I like that. So let's say 14. Now we're back to asking how long is this side and how long is this side? So what we have is a situation where we need the value of x such that x times square root of 2 equaled 14. X times the square root of 2 equaled 14. We need to know the value of x because whatever that is, we're going to put it into this pattern and say it's that times square root of 2 and it's going to come out 14. Does this make sense? Okay. So what times the square root of 2 is going to equal 14? Let's do the guess and check. Let's solve the equation by guessing what x is and just see if it works. What's your first guess? 7. So let's put a 7 here. Well, 7 times square root of 2 is actually 7 square root of 2. What do you need 7 to be multiplied by to get 14?
2.
2. How can we change a square? What can we multiply a square root of 2 by to make it into a 2?
2.
So if it's a square root of 2, square root of 2 times square root of 2 is square root of 4. And the square root of 4 is 2. So this becomes 7 times, let's see, square root of 2 times square root of 2 is square root of 4. And 7 times square root of 4 is 7 times 2. And that sure enough is 14. Check. So what is the value of this side? It's this whole thing right here. Because that has to be put in for x to be multiplied by the square root of 2. So does it make sense that this side is the whole thing? This length over here is 7 square root of 2. You okay with that? Okay. And if this length is this much, how much is this length? Okay. So we basically did a guess and check, and I should have probably left more room here. Let's do another one and another guess and check, but I want to make it slightly more difficult. I don't want this to be even, because that set us up to multiply 7 times 2, and we created that 2 by putting in another square root of 2. Let's create something a little bit more difficult. Let's say 15. So, same situation. X times the square root of 2 is going to equal now 15. We need to know what to multiply by the square root of 2 to get 15. Louder. I like the radical 2, because once we've got the radical 2 in there, this is going to become 2. And that solves the radical problem, right? So now we're multiplying something times 2 to get 15.
7 times 5. 7.5.
7.5?
Mm-hmm.
Okay. Because 7.5 would be 14 plus 1 would be 15. I don't want to drop a fraction in here though. Probably I'd rather drop I don't want to drop a decimal in. Sorry, I said it wrong. I don't want to drop a decimal in. I'd rather drop a fraction into this.
7.5.
How do I write 7.5 in a fraction? Okay, 7.5, and convert that back to, wait, isn't this a mixed number? Convert it back to an improper fraction. Do you remember how to do that?
15 halves.
Good. Isn't this 14 15 halves? Because we did 2 times 7, remember that is 14 plus 1, and put that on top, 15, and put it over the denominator. You remember that from way back when? So the 15 halves, I'd rather have that in here. 15 halves. And I'm going to bring it back to this, to include this, to have this thing here. 15 halves square root of 2, and another way to write that might be 15 square root of 2 over 2. So if this makes sense to you, this whole thing is what we plugged in here, right? We had the original, this one, and then we had the 15 over 2 right here, right there, 15 square root of 2 over 2. That's actually this length, 15 square root of 2 over 2, and if this is that, then this is also 15 square root of 2 over 2. And just to prove it, let's do equation solving. X squared root of 2 equals 15. What do we do to solve the equation? We divide both sides by square root of 2. Gone. We don't like the square root of 2 in the bottom. Remember, we have to rationalize the denominator to simplify that. What do you multiply this by?
1.
Say it again.
Over radical 2.
You're both helping each other. One person said radical 2, the other person said over radical 2. Why do we put it over itself? So that it makes the value 1. Anything times 1 does not change that value, so this is still legal. It's still there, it's still whole. It's like the difference between if you multiply $5 by 1, right? You still have $5, right? So what does this do? This says 15 radical 2 across the top. And it says over radical 2 times radical 2, which is radical 4. And we simplify the radical 4 on the bottom, and we get 2, and that matches this answer here. Now, a common mistake students will try to make, they're tempted by the fact that there's a radical 2 here and a 2 here. Can we divide those to reduce them? And the reason is they're not like terms. Right? These are not like terms, and that will create a problem if we try to cancel one out with the other. So we just let them sit in there all together. Does this make sense? So now you're into the special right. That's a 45, 45, 90. And now your brain is going to reorganize a little bit. So let's flip the 45 a little bit. What, according to the pattern, what would be the pattern value or ratio value on this side?
X.
What would be the ratio or pattern value on this side?
X.
Okay. And that leaves, by process of elimination, the x radical 2. And notice we need the hypotenuse, we need the hypotenuse to be the longest side. So x times the square root of 2 is a larger value than the x's, and that makes sense that it's in on the hypotenuse. Okay, that's it.